Hello everyone, I'm Ghanshyam and today I'll be presenting our work on sequence to graph alignment using gap-sensitive collinear chaining. So, pangenome graph is an alternate way to represent a reference genome in which the variations are represented as alternate string walks. Each walk in a pangenome graph spells underlying haplotype. Now to perform a genome resequencing, taking a pangenome graph as a reference, we need to perform sequence-to-DAG alignment. So I'll start by formally defining what is a sequence-to-DAG alignment. So in a sequence-to-DAG alignment problem, we seek a path in a DAG such that the sequence spelled by the path minimizes the edit distance with the query sequence. So the optimal sequence-to-DAG alignment is upper bounded by big O of number of edges in a DAG times of length of a query sequence. So just take an example. For a human genome, the number of edges is nearly 10 to the power 9, and the length of query sequence is nearly 10 to the power 4. Hence, the algorithm is not scalable. So what is the solution now? The solution would be to use heuristics. In commonly used heuristic, we use a seed filter and extend. So in seeding stage, we start by finding a sort k-mer matches between a DAG and a query sequence, and we call them as anchors. Now, due to the repetitive sequences in a genome, we'll have multiple false positive anchors. Now, in the next stage, which is a filter stage, we start by filtering out these false positive anchors. And in the last stage, which is the extend stage, we extend those remaining seeds to get a final base-to-base alignment. Now, in our work, we'll be focusing on the filter stage. Now, I'll start with a simpler case, collinear chaining between sequence to sequence. So formally, given n seeds as an input to the algorithm, we want to compute a chain, which is an ordered subset of anchor, which satisfies two conditions. First is a precedence on anchor. So here we say anchor 1 precedes anchor 2 if anchor 1 will occur before anchor 2 on both sequence and query. So based on this definition of precedence on anchor, we'll have multiple chains. We'll pick one which will maximize the objective function defined as a score. So the intuition behind this objective function is, so weight is equals to the number of matching bases on anchor, so which is interpreted as a reward, while gap can be interpreted as a penalty to our objective function. So if we'll maximize the score here, we'll get an alignment corresponding to anchor 1 and anchor 2 because it will incur a less penalty. Now, Makinen et al. Decomposed a DAG into set of paths, and he extended sequence-to-sequence collinear chaining to sequence-to-DAG. So formally, given n seeds as an input to our algorithm, we want to compute a chain which satisfies the precedence on anchor. So we say anchor 1 precedes anchor 2 if there exists a path from anchor 1 which can reach anchor 2. If anchor 1 and anchor 2 lies on the same vertex, then anchor 1 should occur before anchor 2. Based on the precedence definition of anchors, we'll have multiple chains. We'll pick one which will maximize the objective function defined as score. Now, if you see here, we are only maximizing the weight, which is equals to the matching basis. Now, we define a gap on a graph and gap on a query sequence, and now we are penalizing that. That forms the basis of our work. So I'll highlight the contributions of our work. So given n is a count of anchors and a is a width of a DAG. Earlier works, they are solving the collinear chaining between sequence and DAG in a polynomial time, but they are not accounting for a gap. In our work, we are also solving the collinear chaining between sequence and DAG in a polynomial time, but we are also incorporating different gap cost. So based on these theoretical numbers, we have developed an open source tool, which we call minichain. And we have benchmarked the minichain against all the existing tools for a human pangenome graph, and minichain achieved highest alignment precision of 98.7% among all the existing tools. Now, if we want to define a gap in a sequence, it's simple arithmetic operation. But if you want to define a gap on a graph, it's challenging. So just take an example. There are n choose two pairs of anchors among which we want to find a distance. To talk about the distance in a graph, the first thing that comes in our mind is shortest distance. So if we want to use the shortest distance as a gap definition, we have to compute all pairs shortest path, and which will incur the time complexity of big O of n times v plus e plus n. and that we have to solve for each query sequence. Hence, it's not scalable for human pangenome graph. So what is the alternative then? So the alternative would be to define alternate definition of a distance. So to define alternate definition of a distance, I'll define a definition of last to reach. So a vertex last to reach v, comma p is the last vertex on a path which can reach to a vertex v. So just take an example. Vertex u is the last vertex on path 1 which can reach to a vertex v which is lying on a path 2. So we'll use this last to reach definition to speed up the computation. So given anchor q precedes anchor p, we'll start by traversing a path from anchor q to the last vertex u on a path 1, and from that last vertex u, we'll compute the shortest path between u and v, and the total path is defined as an alternate definition of a distance. Now, in the pre-processing of a DAG, we start by computing a width of a DAG and corresponding set of paths, and followed by that, we compute a vertex last to reach v, comma p for all the vertices on all the paths. At last, we compute the shortest distance from a vertex last to reach and to a vertex v for all the vertices and on all the paths. So in our paper, we have proved pre-processing of a DAG requires big of k square v plus k time, where k is the width of a DAG. Now, given a pre-processed DAG, on each path we maintain a range tree. So just take an example. For green path, we maintain a green range tree. For pink path, we maintain a pink range tree, and so on. Now, based on the precedence definition of anchors, we'll have two possibilities here. The first is that where both the anchors are lying on the same path. So anchor q precedes anchor p, and both are lying on the same path. So in that case, we'll directly query the optimal score of the preceding anchors to compute a score of anchor p. The second possibility is that the anchor q, which is the preceding anchor, is lying on a different vertex. In this case, if you want to compute score of anchor p, now we don't have information of anchor q. So what's the solution then? So the solution would be, when you are computing the score of anchor q, you propagate the score of anchor q to all other anchors which are lying on a different path. In that manner, when you will compute the score of anchor p, we already have information of anchor q, and we are solving the problem optimally. So this collinear chaining between sequence to DAG can be solved in big of k and log k time, where k is the width of a DAG and n is the input anchors. Now, the complexity we have big of k and log k in time is for the gap, which is the sum of the gap on a graph and gap on a query sequence. Now, we have algorithms for different gap cost, which is let's take an example. Gap prime is a minimum of the gap on a graph, comma gap on a query sequence, and gap double prime is the absolute of a difference of a gap on a graph and a gap on a query sequence. So for this gap prime and gap double prime function, we can solve the collinear chaining problem between sequence and DAG in big of k and log square n plus k and log k in time. Here the log square term comes from the fact that unlike one-dimensional range tree that we have used for the gap, we are using a two-dimensional range query now. Till now we have talked about algorithm and theoretical numbers. Let's talk about the implementation details. So mini-chain is end-to-end long-read aligner to a pangenome graph, which has 3 stages. First is a seed. So seed, we perform WK minimizer sketching. In a filter stage, we pre-process the DAG parallelly. We take a pre-processed DAG, and we perform the filtering or collinear chaining stage parallelly on each read. We compute a multiple base chains for each read, and we push it to a graph wavefront algorithm for final base-to-base alignment. Till now we have discussed about algorithm and implementation detail. Let's benchmark the tool on a real dataset. So for that, we have taken 95 human pangenome graphs from HPRC, and we built a graph. So just for instance, 95 DAG is built from the 95 underlying human genomes, which has nearly 600,000 vertices and 800,000 edges, which has nearly 300,000 structural variants, and width of the 95 DAG is nearly 35. So that justifies the fact that why we have bounded our algorithm in terms of the width of a DAG. Till now we have a real pangenome graph, but we want to evaluate the performance of a tool. And for that we need a ground truth. To get a ground truth, we have taken one of the genome and we have simulated a read with a 5% error rate with an N50 length of 10 kilo base pair. So this forms our benchmark dataset. We'll use this and benchmark all the existing tools. So here we have precision recall curve. On the y-axis, we have percentage of aligned reads. And the x-axis, which is on the logarithmic scale, we have percentage of incorrectly aligned reads. So minichain is our tool. We have compared minichain against minigraph, graph aligner, and graph chainer. So as we can see, like in precision recall curve, we want a top left. In the sense, we want to align more and more reads with a lesser number of incorrectly aligned reads. So as we can see, even we are increasing the size of the DAG, we are constantly outperforming all the existing tools. So this is for accuracy. Now let's talk about the runtime of the aligners. So if you see, minichain is not performing best, but still the alignment time and memory limits are well within the practical limit. Now key takeaways are, we proposed the first work which formulated a sequence-to-DAG collinear chaining, which incorporate multiple gap definitions. Based on these formulations, we have proposed an efficient parameterized algorithm on terms of the width of a DAG. And this algorithm lead to more accurate read alignment. And minichain is open source tool. One can go to our lab's GitHub repo and one can download. Thanks. I'll be happy to take questions.